So power factor correction. You know, guys, if you have a commercial building and your power factor why do we care about power factor to start with? Anybody knows? Who cares about power factor? Well, if you, well, that's if you're environmentally friendly, tree hugger like Chad. But if you are like, whom am I going to pick? Like Zach, for example, non-environmentally friendly, non-tree hugger. So why should you care? I'm picking on you, Zach. I know you are. You care about the rabbits and the deer and everything else. So if you don't care about the rabbits, the deer, and everything else in the wilderness, and holes in the ozone for energy, why should we care about the power factor? How many of you guys don't care about spending money? Anybody has an unlimited amount of resources and you can spend money whenever you want? We all have a limited resources, so we care about our dollars, right? All of us, except Adam. Except Adam. So the power factor, guys, if you have a low power factor in your building, long story short, the electrical utilities will penalize you financially for this if you don't correct it. That's why we care about the power factor. Commercial building only and industrial, Zach, and Andrew. So that's why we care about the power factor correction. Okay, so let's go ahead and talk about this magical power factor. We want to talk about the concept of power factor, guys, why power factor is important. Power factor situation with correcting. When we have a power factor, guys, we'll talk about what's a power factor first, and then how do you correct the power factor. When you correct the power factor, you correct it in two ways, either by adding big fat hamburgers. Anybody knows what a hamburger is in terms of beef and bun? Yeah, but instead of having that one, beef and bun, you have a capacitor. I call it hamburgers. You add basically hamburgers into your system, a capacitor, right? That's what a capacitor is, beef and bun. And then, or you can have a synchronous motor, synchronous condenser or motor that also can correct your power factor. We'll talk about this one in a second. Okay, most of the loads that we have, guys, as you own, a lot of loads are resistive load, solely of resistance. Very few of the only load that's purely resistive is heaters. Anything, boilers, heaters, anything that convert electricity into heat is a resistive load. Inductive loads, guys, like large motors have an inductance in them. If you guys look at all the loads that we have in our project, I would say 75% of them are inductive loads. All the motors, right? All your motors are inductive loads. So and they do have a tiny little bit of resistance for the coil, but for the most part, it's a coil, inductive loads. And I'm not going to go back to the inductance and reactance and so forth. The last one is capacitive loads. Capacitive loads, guys, typically it's not a load, it's added feature to the power system to correct the power factor. You add a capacitive load to correct your power factor. So if you graduate from here not knowing that there are three types of loads, the resistive load, the capacitive load, and the inductive load, ask your friend Chad for a refund. Because you guys spend a lot of time with Mr. Ryman talking about this. Okay, the power factor. The power factor, gentlemen, is a ratio between the true power that you use divided by the apparent power that it appears to be coming to your building. It's always the cosine of the angle. We'll do a couple of calculations, guys, for it. Your power factor can be from 0 to 1, either leading or lagging power factor, And the definition of your power factor, like I said, is always the watt over the volt amps. And for calculation, Andrew will be doing a lot of calculation later on related directly to this topic. I didn't synchronize myself. It's Monday morning, huh? Okay, so see if I can write. There you go. Now I can write. Okay, so that's so when you define your power factor, it's always there you go. It's always the watt over the volt amp. Your watt over the volt amp. Your power factor can go from 0, you would hope you would never be there, into 1. If you have a 1% or 100% power factor, you have a purely resistive load. 99% of the time, Andrew, your power factor is below in the 90s. If you can maintain your power factor between 90 and 97 in your plant, you're good. You don't want to go to 100 because if you go to 100 when you turn certain loads off, what's going to happen? your power factor swing to the other end. It becomes from leading into lagging power factor, and that creates high voltage in your building that you don't want. So be aware of that one. In terms of here's the power triangle. This is a quick reminder of the power triangle, guys. Here's my resistor over here. I have this resistor is 0.5 ohm. This is inductive reactance. Remember the XL with Mr. Ryman when you guys were there, 0.6, and this is my Z. Z is it looks like it's 0.781. So when you have an AC system, the actual impedance of the system is made of the resistor and the inductive reactance. And I'm just going to quickly remind you of Pythagorean theory that says to find the Z, you square the R and add it to the square of the XC. Do you guys remember that from Mr. Ryman's days? So that's how you find the impedance of the system. This is your impedance of the system. This is what cooks your meal here, the one that you want to increase. This one is the offender. This leg here is the offender, the one you want to minimize. That screw up your power factor, right? And the power factor is right in here, as you can see. That's my power factor, and the Q or cosine. So if you take a cosine 50 in this case, that will be your power factor. I don't know if they're giving it here. Cosine 50, that will be your power factor. This is called impedance triangle. You should have worked on that one when you were in first quarter. Impedance triangle, guys, where you take the XL, the R, and the Z, and you find the power factor from the Z, XL, and R. Any comments, guys, about this one? Typically, that's not what we do when we correct the power factor. We use the power triangle. This is not a power triangle, the impedance triangle. They're all the same. There are three triangles, guys. There's the current triangle, actually four. The voltage triangle, the current triangle, the impedance triangle, and the power triangle. The most famous one is the power triangle, right? They're all the same triangle. All of them are the same triangle. So if you take the R here and you multiply it by the current, and you multiply this by the current, and you multiply this by the current, you got the voltage triangle, right? If you multiply it also by the voltage, and multiply here by the voltage, and multiply here by the voltage, now you have a current times voltage. So you multiply it by the voltage, and in this case, only the current. You don't take the impedance. Just take the current with the voltage. Don't take the impedance with that. Take the current and the voltage. What do you get? The power triangle. You get the power triangle. So that's how you get the power triangle, impedance triangle, current triangle, and voltage triangle. The one that we're going to be working, we emphasized this one in the first quarter, guys. The one I'm going to be working with you being grads now is the power triangle. Okay, power can be determined by, so we'll do the calculation later on the power triangle, but how do you calculate the power triangle? Kerry, if you get into any commercial industrial building right now, the utility will get you a meter, 1 or 2 meters. If there are 2 meters, one will be measuring the kVAR in your building, and one will be measuring the kilowatt hour. Or 1 meter that can give you both readings, give Excel both readings in your building, the kVAR as well as the kilowatt hour. And based on the kVAR and the kilowatt hour, they can decide what the power factor in your building. And if your power factor is maintained below 90 for a certain amount of time, you will get a letter from them saying you have been penalized and you have to improve your power factor. That's how they maintain it. So how do you do the power factor? Here's my power factor. You can have a power factor meter. So most of the time, guys, multi-function meter or digital meter, you have a 1 meter that can give you kilowatt hour, VARs, power factor. You can get the harmonics out of it. You can get the current, the voltage. That's what customers do if you go in a hospital or a sport arena. Inside your switchgear, the owners will specify a multi-function meter, just 1 meter. And this multi-function meter, guys, Square D and all those manufacturers have their own brand of it. It can give you everything you need to know about your power system, as in what's the voltage, what's the current at every moment, what's the power, what's the kilowatt so far, what's the VAR, what's your power factor, what's your harmonics, and the level of your harmonics. So, but in order to calculate the power factor, you need a power factor meter. If you don't, here's option 7.
How is harmonics measured? Is it just variance, percentage of variance?
If we have a class about harmonic, we'll talk about this one. But it monitors, yeah, it takes the signal, analyzes the signal. What is harmonics? So harmonics is multiple signals combined together at different frequencies. So that digitally, you separate these frequencies and you average them to get to the, what percentage of your signal is harmonic. But we'll talk about this one. Okay, so you have power factor, then, or you can have a kilowatt hour and kilovar meter and kilowatt hour meter. That also gives you the power factor. Or you can have a watt meter and kilowatt meter in combination with a voltmeter and amp meter. That also can give you the power factor. Any comments, any questions about how to measure the power factor? Either you have a big fat. Now, the common things therein is to have a power factor meter. Not a meter. It's a function in a multi-function meter. One big digital meter that can give you multiple things. Among them is the power factor. Among them is a power factor. Any comment, guys, about how measurement, at least being able to measure it? I will remind you to find your power factor. What you need is kilowatt over kVA. If you were able to measure your kilowatt, and if you were able to calculate your kVA, then you can find your power factor. Any comments, guys, about measuring and or calculating your power factor? What quantities do you need? So these are the quantities that you need to calculate them. This is one of the single most important tables that you guys are going to see. We will work on this one tomorrow in the calculation, but I want to remind you guys that kVA equals the square root of kW squared plus kvar squared. So this is my kVA, and this is my kvar, and this is my kW. That's so-called power factor correction of power triangle. This is your power triangle. So the power triangle, guys, is made out of the kW, the kvar. When you add them vectorially, this is how we add them. We add them vectorially. So here's my this is my kW. Here's my kvar. When you add these, you end up with the apparent power. You end up with your apparent power right in here. And you guys have seen this power triangle before, right? You've seen the power triangle. So what I'm going to do tomorrow is we use the power triangle to correct the power factor for a system. Any comments, guys, about this piece is called the true power. This piece is called the apparent power. And this piece here is called the reactive power. Which one of them, the single most important one that cooks your meals and boil the eggs for you in the morning so you can eat eggs instead of eating cereal? You guys eat cereal or eggs in the morning? Two different people, either cereal or eggs. I'm the egg person, huh? And in order to boil your eggs in the morning, which one that boils your eggs here? The kilowatt. The kilowatt is the one you at Excel, we, the consumers, we pay for the kilowatt. So what does this do for a living then? This is there, guys, magnetize the system, make sure that motors work. So I call this, the bars are necessary evil. It's there just to magnetize the system. You need it to magnetize the system, so ultimately minimizing it is the best way to do it. Okay, so if you guys look at this example that they're giving, they have 1075K. If you square the 796 square plus the, what was that, 720 square, you're going to get this value. So we have 796 kilowatt true power and 720 kVAR. When you, to find the kVA, you have to square them and take the square root of the two. You get you 1075 kVA. If you take the 796 kW, divide it by the 1075 kVA, That will get you my power factor. And they have it here. Where's the power factor? Somewhere here. And that's the number 0.74. Now you take this 0.74 atom to town and you get penalized. If that's your building, you're screwed up. You're going to get penalized financially for this low power factor. So tomorrow, we're going to be taking a couple of examples how to correct this one, how to correct the power factor. Any question, guys, about the apparent power, the reactive power, the true power, apparent, reactive, and how to calculate them for Pythagorean theory? I hope that at least the formulas are familiar to you. And then they have the angle here. The power factor is always the angle between the true and the reactive. Your true and reactive. Here's the cosine of the angle. Will get you the power factor, the cosine. And you guys have done trig in 10th grade, Darren? Trig, you find the power factor cosine of an angle, the adjacent over the hypotenuse, right? Here's my adjacent here over my hypotenuse. That's the only time probably in this class we touch trig. Any comments, any questions? Any comments, any questions? So that's basically your power triangle. Now, because that sucked, look what they did, guys. They added a capacitor bank. I added a capacitor bank. So I have actually a synchronous motor is added. So look what happened. I added a synchronous motor of equivalent to 520 kbar. And when I added it to the 720, ultimately my triangle shrunk. That's what we did. My triangle shrunk. My true power continued to be the same. Then my apparent power also got smaller. Can you guys see what happened to, instead of my true power being here, I got this leg to go down. I don't know if you can see that. So what they did is they added a condenser to the building. That's what we're going to do tomorrow. Add a condenser to the building. The value of the condenser was to correct the power factor, you have inductive reactance. To counter the effect of inductive reactance, you add a capacitive reactance. So what do they do for a living? One push to the east, one push to the west, or one north, one south. And what happens if you have two forces pushing against each other and they're equal? Right? Against each other. What do? You equal yourself to a force of what? 0. If one of them is bigger than the other, it's going to push you in this direction, equivalent to the difference between them. So here's the K bar left in my system is 200. Here's my KW, and then my new KVA, system. Jeff, my friend, is 821 kVA. My new KVA system is 821 kVA. So I was able to reduce it from almost 1,000 into 821 kVA. Any comments, guys? Any questions? Any comments? Any questions? I will go over the calculation in details, like I said, tomorrow. But when you add the capacitive a bar, this is my capacitive, and this is my inductive. These will push against each other, guys, in the opposite direction. So what do? They subtract each other. So by doing this, look what happened. I reduced my K bar into 821. My power factor is increased to 97%. Excel is happy. I am not penalized. I'm not paying more money. So everybody's happy, right? Any comments, any questions about power factor correction?
So is the larger the motor load, the more distance you kind of want to have from the 100%, just because you'll have more fluctuation?
You do, yes. You when you have your motors, you want to correct between 93 to 97.
So if you have like almost no motors, it's 98.
If you if you have no motors, then you have your power factor. No need for correction anyway. Your power factor will be in the 90s. The only time you correct for power factor, if your power factor dips below the 90, then you need to correct. If your power factor by itself is 90 plus, no need for correcting for power factor. Any comments, guys? Any questions? We'll take an example like this tomorrow in details how to calculate it. But that's the added this. When you correct power factor, guys, there are two ways of correcting power factors. There's adding capacitors or adding synchronous motors. Synchronous motor, guys, are special type of motors that they put DC in the guts of the motor. By overexciting them, they start creating VARs. So correcting power factor happens in two ways, Adam. One is a capacitor, and the other one is what? Condenser, so-called condenser. So rotating machines with no load, typically no load. Can you guys see that? No load, no mechanical or electrical load on it. It's spinning. The rotor is spinning there inside your building, and they overexcite these synchronous machines, and they start generating VARs for you. So that's what the concept of this one. So overexcited, putting more DC into the rotor, it starts creating a leading current or a leading VAR, and that leading VAR counter effect the lagging VAR that's coming out of the other motors. The stronger the normal current leading kVAR, counter affects the lagging. This is how it works. It counter affects the lagging kVAR. For example, I have a 10 kVAR leading and another 10 kVAR lagging. You put them against each other, the outcome is big fat 0 kVAR, not leading, not lagging, right? They push against each other, they neutralize each other. Any comments, guys? Any questions? Any comments, any questions? Examples coming tomorrow. Detailed example about the calculation is coming tomorrow. Okay, here's how synchronous motor works. A lot of you heard of DC motors, a lot of you guys heard of capacitors. When you use a synchronous motor, what they put, guys, right here is they put DC. So they put a DC, so by increasing the voltage, so let's just say 50 volt, here I'm just throwing this one to 150 volt, DC. So they are adjusting the voltage here. They're putting more or less voltage. The more voltage you put here, right, on this synchronous motor, the more VARs the synchronous motor start creating. That's how synchronous motor works. And here's your control system for this without getting into the details. Here's my power factor. They have a bunch of power factor relays. So it senses what the power factor is and adjusts the DC to get you this amount of VARs to maintain the power factor this amount or this amount, because the load fluctuates in your building. So that's your control system for synchronous motors. What do synchronous motors do for a living? They spin the rotor, nothing on it. They spin, they get them overexcited by putting more DC on them, on the stator, on the rotor, and then they get you a leading power factor, Any comments, guys? Any questions about this? Any comments, any questions? Overexcite the synchronous motor, get you VARs that you can correct. Here's a very good example, guys. I have two synchronous condensers. Together, they're generating 520 kVAR. What I would like you guys to look at is right here. So here's the power that I have in my building. Let's look at the VAR here. Here's my VAR. I have 720 kVAR, my kVAR, and I'm injecting right at this point, correcting the power factor. So look what happened if you have 720, subtract 520 from that. That will leave you with 200 kVAR, right? And this is what's left over after I corrected the power factor. Can you guys see that? Right at this point, when you added them, these came in here. They knocked down this number only. They reduced it, and by reducing this number, the kW, if you look at the kW stays the same. Can you guys see the kW? Where is it? The kW here stays the same. The kW stays the same. The only thing that changes is the VAR, and because the VAR changes, the kVAR has to change. So this went from 820 down to 821 from 1075. 821 to 1075. And you increase and you corrected your power factor to, what is it, 97, that example. So that's how they tie them right in here, the power system, and they correct your power factor. They knock down your kVAR. They don't do anything to your kilowatt hour or kilowatt. Your true power stays the same. The only thing that they deal with is they knock down your they knock down your your K-bar. They knock down your K-bar. So I just want to emphasize one little thing here. They don't increase or decrease your kilowatt hour. You don't touch it at all. All what their job is to take the bad offenders, K-bars, and reduce them. So if you look, I want you guys to look at this because that's, if you don't see that one, it's really hard to understand it. Here's how much I introduce, 520. Here's how much I have in my system, lagging power factor. These are leading. Can you guys see the leading and the lagging here? When you added them together, they're opposite directions, so actually subtracting them, they added together, they went and reduced down to what? To this value.
So it's actually using the 520 K bar to run them?
What they do is they offset each other.
Because something's got to make them spin, right?
Make what
To
spin?
make them operate?
Yeah.
Synchronous.
Yeah. So, the electricity, you're powering them, so they're spinning them with some juice. You're getting some juice to spinning them, but by overexciting them, you're creating counter K-var, counter inductive reactance, or in this case, capacitive reactance, leading power factor. So
I was just wondering what their input was to create the spin, to create the counter K bar. Is that just using the inductance?
they're using tiny little bit of power to spin.
So it is using
When you get the spinning, and you put DC into the synchronous motor, by design, the magic of it, it starts kicking back VARs, adjusting your power factor. Kicking back VARs by adjusting your power factor. We'll get into the guts of how it works, but I'm interested more in, guys, if you have a synchronous motor giving you this amount, it will knock down your VAR in your building. It knocked down your VAR in building. So tomorrow, when I have an example for you, and I say I'm adding a condenser or capacitor, that's what it does. It knocks it down to this, to subtract it, basically. Okay? So if I want to have 100 power factor, what do you think this value should be to knock this down to 0? 720. Why didn't I do 720? Because if you correct to 100% power factor, what happened? When your motors are down, you overcorrect. So I'll go over this guy's calculation also tomorrow. Okay, this is a few things about paralleling feeders. When you parallel feeders, we went through this one, guys, a couple of times. When you parallel your feeders, all the conductors must be, all the phase conductors, neutral conductors, equivalent conductors must be in the same conduit. If you use all equivalent conductors, must be in the same raceway. You can't parallel this then number 1 not. And you have to, conductors, one group must be identical. So the length have to be the same. The length of the conductors have to be the same. Length of conductors, insulation, termination, conduit type, all these have to be the same when you parallel your conductors. Any comments, any questions guys about paralleling conductors? This is just set on the side about paralleling conductors because they are paralleling for the condensers. Okay, here's your conductors here paralleled right here. When you parallel them, all the conductors of the same circuit have to be the same, including the neutral and the grounding conductor. Neutral and the grounding conductor. Okay, correcting factors, guys, with capacitors. Capacitor will create a power factor. Capacitor is nothing other than 2 plates. Andrew, my friend, you have 2 plates, conductive plates, and in between them, their insulation. And you put the wires to the conductive plates, you have the insulation, it creates a capacitance, inductive reactance, capacitive reactance. Okay, so when you put them in, you use them to correct your power factor in your system. Couple of things that you have to know about that one. So this is just how to measure the power factor. You need a voltmeter, one of the ways, as well as the watt meters here. Okay, correcting power factor. So we'll do the calculation like I said, guys, tomorrow. But in order to correct, correct in watt meter and ammeter. So in order to correct for the capacitors, you need to know what's your watt and what's your volt amp, right? And that's the only 2 ways you can correct your power factor. So here's my power factor. I need the watt over volt amp. So I need to be able to correct the watt divided by the volt amp. Any comments, guys? Any questions? Summarize. We can correct power factor with synchronous machines or with capacitors. Um, for motors, you can correct the power factor, guys, in two ways. You can correct them by adding them to the switch gear or by adding them to the motors, directly to the offenders. Motors have two types when they design them. The old times, they used to use U-frame motors. They start using T-frame motors. Based on what type of frame for these motors, it decided what size capacitor to offset the work of these motors. The offenders, the reason why we care about motors, Zach, because motors are the most offenders when it comes to the power factor, low power factor. When you correct, Jeff, you always correct not to 100%, between 93 to 97%, because you don't want to end up with a leading power factor. Leading power factor. Okay, so when you have a capacitor, guys, we'll talk about, there's two ways of connecting. When you have a capacitor, here's a capacitor. When you have a capacitor, you can connect your capacitor right in here. If you connect it like this way, guys, the only thing you have to pay attention is sizing this conductor, which is 1.35 times I full load current. That's how you size the conductor for a capacitor. When you size the conductor for a capacitor, you take the full load current of the capacitor and you multiply it by 1.35 from Article 460. Article 460 will tell you, I don't know if we have the section that talks about this one. Article 460 will tell you when you size a conductor for a capacitor, you have to multiply it by 1.35. Any comments, guys? Any questions about that? And two ways of connecting them. If you can connect them on the load side with the motor, right here. Then you have to adjust your overload. Basically, lower it down because now the current is going to be lower, seen by that. And that will solve the problem right at the offender level. Right at the offender level. Any comments, guys, about this? You do not, Jeff, you do not need an overconduction device or a disconnect for the capacitor if you do it this way. If you do it this way, gentlemen, look at this. If you do it this way, then I need to size my disconnect 1.35 times full load current, full load current for the capacitor. My fuse, typically 1.35 times I full load current. If it's not a standard, we go down. My conductors, same thing, 1.35 times I full load current. That's how we size all these conductors that feed your capacitor. And then you take from the disconnect size here, and you have a disconnect for your capacitor. And that will be to correct the power factor right at the level of a motor. Any comments, guys? Any questions about this? Any comments? Any questions? Any comments? Any questions? Two ways. One way is to put it right here on the load side of a disconnect, the load side of a disconnect starter overload protection device. The second way is to connect them on the switch. Which way is the better way? This way is better, guys, because in this case, if this air handling unit is running, the capacitor will be on. If the air handling unit is off, what's happened to the capacitor? The capacitor is off. Any comments, guys? Any questions about that? Two ways of connecting your power factor. Is it Monday or what? A little bit Monday? Okay, I'm almost done. Monday catching up with you. Okay, a few things, guys, about testing capacitor. Capacitors are dangerous. They have a couple of safety things on them. When you put a capacitor, the manufacturers have to provide the resistor. So when you disconnect the capacitor, the resistor have automatically to shunt across the leads of the capacitor and reduce the voltage to 50 or less in certain amount of time. I can't remember the time now. Test capacitors, they have a high voltage potential that they shoot through the capacitor to test them, make sure the insulation is good. So measure the capacitance, you have to disconnect. So this is just a little bit about testing them. When you test them, if we're designing, we don't test them. If you are to test them, you disconnect them, take them out, discharge them. Typically, they will discharge if they're power capacitor by manufacturer. It's code requirement. And then you have to test strength of the dielectric. If you want to do how strong the capacitor is, First, you measure. You can measure that in the capacitance, guys. There's measurement for the capacitance. If you want to measure it, the proper way of measuring it is they shoot a high voltage right through it. It gives you the capacitance is supposed to be this much, and now it's this much. So what's going to happen? This capacitor is crabbing on you. You're going to throw it and bring a new one. So that's measuring a little bit about the capacitor, voltmeter. And the last thing I want to show you, my friends, really is a couple of pictures, very important, before I let you go on a Monday. Mondays are hard. Okay, we talked about these, talked about this, talked about this. Here's the most important thing to get that, guys. When you have a capacitor, what fails is the electric, the insulation inside it. The capacitor, it fails the short. We talked about this. Here's the Kerry, my friend. Here's how a condenser looks like. Can you guys see anything connected to the rotor here? Nothing connected to the rotor. It spins, spins, spins. It just spins and creating bars for you. You don't have an air handling unit connected to it. It's just correcting your power factor. By the way, the project that we have right here, there are two condensing right in here on this project. Two condensers setting to capacitors. Look at the capacitor bank. You can have bank of capacitor, guys, with the controls on them, and you can turn them on and off. You monitor your power factor. There's my friend. You monitor the power factor. When the power factor goes below a certain value, close a set of contacts to put a bunch of capacitors on. And then the power factor keep going down again. Another set of contactor, close this set of capacitors on. And then the second, and then the third, and then the fourth. That's how they control how many caps you can put in your system. Either you put them all at the same time or put them in steps. Put them at the same time or put them in steps. Okay, this is important. I want we're going to be using it tomorrow, guys. So let me flip this one and show you. Can you guys go to this one, please? Because that's important to. Okay, how do you flip this one? You flip it here. Why it doesn't want to flip? Jeff, why do you think it's not flipping? Okay, can you guys see this one? This one will give you a multiplier, how to correct the power factor. I promise you we're going to be using it tomorrow for our calculation. So, does it want to flip? Yucky. Go back. All right, here we go. So anyway, if you guys look at the bottom here, can you guys do me a favor here? These are your original power factor right here. Okay? And these are the corrected power factor that you want to correct to. So if my power factor and my original power factor and how much bar do I need to correct to. So if I want to correct, look at this nasty power factor. If I want to correct to my existing power factor is 50, and I need to correct to an 86. I can't read this one. So that's the multiplier that you need when you size your capacitors. If my power factor is 80, and I need to correct to 87, that's not a good correction. My multiplier will be this value. So I'll show you guys how to use this one tomorrow when we're doing the calculation. But this is very, very important when we find so to find the bar, what they do for the bar equal that multiplier multiplied by the kW of your system. So you take any of these numbers based on what's your original power factor and what do you want to correct to, and you multiply it by the kW, it will give you the size of the capacitor that you need. Can you have a thumbs up how this table works, guys? Because this is important for tomorrow. You take any of these numbers. So if I want to correct my power factor from 50 here into 89, I take this number that I came up with, and that will be my M. And if the kW of my multiplier, say, was 1,000 kW, then you put that number here, multiply it by 1,000, and that will get you how many VARs you need to correct in your system. That's correcting at the switchgear level. At the switchgear level. What's correcting at the switchgear level, Jeff? Here's my switchgear that you guys sized with your friend Chad here. So here's multiple loads going on, multiple loads. and I want to correct right here. So guess what they do? They take an overconduction device and put a big cap, kVA bar, and they put a cap. Can you guys see that? They put the cap right at the switch here. Here's my 4,000 amp switch here that we're designing for. They put the cap right there. That's when we went to, where did we go? When we went to Boston Scientific, did you guys see the capacitor right at the top of the switch here? That's exactly what we're talking about. That's how we size it. That's the poor man's job. Why it's the poor man's job? Because you're correcting right down at the surface. The rich man's job is multiple correction. This is poor man's job. Let's go look at one time, and I'm done. I promise you. I can see. Let's do the rich man's job. The rich man's job, guys, is to go by the offenders, right by the offenders, and correct the power factor. So look at this. These are two tables. We're going to be using them tomorrow, guys. Same thing. Let's do a T-frame. So take this. Here's an example. If your motor, where's my friend? I have one friend or two here at least. Where's my friend Aaron? Do you remember a horsepower of one of the horsepowers that we have in our building? What is it? 60? What was the air handling unit? Was it 60? Anybody remember? Let's say 60. I have a 60 horsepower air handling unit, right? 60 horsepower, and I need to correct the power factor. And almost always, it's typically they're running at close to 1800. The synchronous speed is 1800 RPM, and almost always, Jeff, they are a new equipment is T-frame motors. They make them. They call them T-frame. The old RU T-frame motors. Almost always you have to correct to these two values, 94 or 93, 297, not 100, okay? And I need to correct the power factor for this. Without doing any calculation, without using the table that we did before, if you go across, it will tell you the K-bar, you need 18 K-bar right here from the get-go, 18 K-bar capacitor. You need 18 K-bar capacitor. Can you guys see that, how this table works? You take the horsepower of your system. This is for 480, the horsepower of your system, and the most common, this is the most common speed, synchronous speed. From there, oops, this is actually, I'm off. Am I off here? Yeah, I'm off by 1. So that will get you K-bar. That'll give me a 20 K-bar for this system. So now I know what the capacitor size is. So I put my capacitor and go put my fuse and my disconnect and bring it all the way to, here's my motor, tie it right here. Here's my disconnect for my motor, and put it, here's my overconduction device, my controller, my overload, and here's my motor, the 60 horsepower motor. And what size this baby will be? 20 K-bar. Does that make sense? Here's my 60 horsepower. That's how we size it for motors. We will be using this table tomorrow, my friend. Any comments, any questions about this? Straightforward, huh? The last thing I'm going to show you right at the bottom here, before I go, can you guys see right at the bottom, right here, please? It says, for maximum benefit, locate at motors for 208 voltage, use, what did it say here? Anybody can read that? This table is for 480 system. For motors that are running at 480. What if your motor is running at 208? How do you need to adjust it, Jeff? You take the numbers that you got here and up them 33%. Any comments, any questions about this table? Any comments, any questions? So that's how you correct the rich man's way, meaning you will have multiple capacitors right by the offenders. Right by the offenders. The last thing I'm going to do, and I promise this time will be the last thing. The last thing, my friend, is if you go to, they have a table in your book that actually tell you the sizing right from the get-go. So Take this, Jeff. If you have, where's the 20? Look at the 20. Here's my 20 kVAR that I sized. Here's the full load amp for it, calculated. Here's the wire, the number of size, THW wire size, number 4. And here's the fuse that you need. And here's the disconnect that you need. And here's your normal amps for this baby. Your normal amps for this baby. No, this is not the second size. Nominal amps. Okay, so the 480. So that's basically the, if your this is if your voltage is running at 240. So this is, you have to cut it right in here. There you go. Does that make sense, guys? So if I have, if my system is 480 like ours, then here's all your information that you need to size. So let me ask you, Brian, my friend, if I have a 20 kVA capacitor, the full load of it is 24, the conductor size is number 8, the fuse is 40, and the disconnect is 60. Already sized for you, no question asked. So what I'm going to do with you guys tomorrow, I want to show you how to size it, but the table is already there. So how did they find the disconnect, guys? Here, they took 1.35 times the full load amp. And the fuse, typically the same thing, and the conductor, typically the same thing. From the 1.25, they did the calculation for you there, Jeff, my friend, and put them in the table. Any comments, any questions? Can you have thumbs up, Chad? We know how to use these two tables, because that's what I'm going to go over tomorrow. And it gives you 3 voltages, 3 common voltages for motors. If you don't have this table, you can always use a 1.7, 1.35. Any comments, any questions, guys, about capacitors? Comments, questions about capacitors? Okay. Okay, that's all we have. A lot for Monday, more or less. Okay, I'm going to give you guys 10 minutes, and I would like to show you a few things in Revit, how to drop families and circuit them. Thank you.